Okay, so we are actually discussing quotient groups. Today we had to go over some properties of quotient groups. Let's go over the definition real quick. You have a group G, and let's take any normal subgroup of G. Then G over N denotes a set of all left cosets of N in G. So G over N contains all left cosets of N in G. And then we define the binary operation star, which we actually later drop writing G1n star times G2n. We simply adopt G1n times G2n, that convention, right? So how do we define this binary operation? We simply take any two left cosets, apply this star so that what we get is the product of the two representatives, G1, G2 times n, which is also a left coset in G. And we saw that this is a well-defined binary operation. And what you have over here, G over N, together with this star, is a group, which we call the quotient group. Right. We went over some examples. Then properties of quotient groups. The proof of the first one we finished. Let G be a group, and let's take N to be a normal subgroup of G. Then G over N, we have the quotient group G over N, which we can define because N is normal in G. If G is abelian, then we have this quotient group also to be abelian, right? Which we proved last time. So the second property, if we have G to be a cyclic group, then the quotient group must also be cyclic. Let me write the second one. If G is cyclic, then the quotient group G over N is also cyclic. Is cyclic. Right. So how do we prove this property? Right. So once again, if J is cyclic, then G over N, the quotient group, must also be cyclic. Right. So how do we prove this one? We are given that G is cyclic. In other words, it must be generated by one of its elements, right? So let's take it to be simple G. Let G be generated by G, an element in G, so that we can write G as being generated by G. Now what we want to show is that G over in the quotient group is also generated by an element that's in there. What sort of elements do we have in this quotient group? All left cosets of N in G. So it has to be a left coset of N that is generating this entire group. We already have this statement written down. G is generated by this one element G. So now what we're going to do is we will show that the left coset of N by this element simple G is the left coset that's going to generate this entire quotient group, right? So we will show that every element of the quotient group G over N is of the form Gn to the power of k for some integer k. If an arbitrarily chosen element takes this form, if you can write it in this form, this simply means that any element can be written in this form. The entire group is generated by this one left coset Gn. Okay, now let's take an arbitrary element from here. Suppose G1n, where G1 is taken from G, is an element in the quotient group G over n. Now, like I told you, G1, the simple G1 is an element in G, and G is being generated by this simple G. Any element that you take from the group must be some power of this simple G. So we must have G1 to equal G to the power of K for some integer K. Because G is a cyclic group and this G1 we are taking from the group G. But observe this, Gn to the power of K is equal to, we can expand this product and write Gn times Gn until you have K factors of Gn. So in this product, we have Gn K times. And this is equal to what? Simply using the definition of the binary operation over the quotient group, we can write this as G times G times G n. Once again, how many G's do we have in this product? K, right? In other words, this is simply G to the power of K times n. And we know from here, Gk is what? G1 and n. So G1n, which is an arbitrarily chosen element in this quotient, takes the form Gn to the power of K. Therefore, any element, right? Let me write, since is chosen arbitrarily, from the quotient group G over n, any element in G over n can be written in the form Gn to the power of K for some K, for some integer K. Therefore, Gn, the left coset of n by this element G, this simple G is the generator for the group G, generates the entire quotient group. It generates the entire quotient group. Right. So we can write Gn as being generated by simple Gn. Okay. Do you have any questions?
No, ma'am.
Right. Now, let's consider the additive group on integers z and let's take n to be the subgroup simply contained in the identity. This is a normal subgroup in Z because we know for any group, abelian or not, the group itself and the trivial subgroup will always be normal in that group, right? Anyway, Z is an abelian group, so no matter which subgroup that you take, it will always be normal in Z. We know that N is a normal subgroup of Z. Now let's find the quotient of Z by this trivial subgroup, right? So we are going to find what a type of elements the quotient contains. This is simply Z quotient, take the quotient by the trivial subgroup, and this contains all left cosets of the trivial subgroup by elements in Z. Hold it. I just wanted to make sure that we didn't do this example last time. Okay. So what sort of left cosets does it contain? How do we define the left coset if I write it separately down here somewhere? If I take n to be an integer, n times the subgroup, the trivial subgroup, this is the left coset of this trivial subgroup by the element n. This is equal to take n and any element in this group, and now in this case we have only one, but to write it in a proper way, I will simply write m. N times m. So times, when I say times, the product actually refers to the binary operation over the group, in the group. This is the additive group. So what is the binary operation? Addition. So between these two, we have addition. Here, m comes from the trivial group over here. So this is these are the elements that are in this left coset of the trivial group by the element n. N is chosen arbitrarily, right? And this is equal to what? N times m is, we only have one option for m, which is 0. So n plus 0 is simply n. What do we have in this case? Simply that singleton set containing this element n. So how many left cosets are there? An infinite number. And what are those left cosets? All these singleton sets. If I specifically take n equals, say, 1, then 1 times, sorry, let me write it, n times this trivial subgroup, which is equal to 1 times the trivial subgroup, is simply equal to the singleton set or this one element set, where this one element is actually the integer 1. If I take n to be -2, then we have -2 times this left coset of the trivial subgroup by this element to simply be this singleton set. So what sort of elements do we have in the quotient group? All the singleton sets, all the one element sets, right? So we can write it as simply these elements. Now this set is an element in the quotient group, okay? N is an integer. These are some of the elements that we have calculated which belongs in this quotient group. Okay, so now observe, when you take this quotient, right, you get all these singleton sets. For n equals 1 or the integer 1 in Z, you have a corresponding element in this quotient, which is the singleton set containing 1. When you take n equals 2, once again, you have a corresponding element in the quotient group, which is this singleton set containing 2. Likewise, there is a one-to-one correspondence between this quotient group and the group of integers itself. So it's easy for us to see that Z is actually isomorphic to this quotient group, right? We simply take an element over here and map it to its corresponding singleton set. It's a one-to-one, there is a one-to-one correspondence. This is an isomorph. These two are isomorphic. They have essentially the same structure, right? Now observe, this is when we take the normal subgroup to be the trivial subgroup. What if we take the normal subgroup to be the group itself? Because like I told you earlier, for any group, abelian or not, the group and its trivial subgroup will always be norm, right? So let's take n to be Z, right? Z is a normal subgroup in itself. Now let's take the quotient of Z by itself. This contains all left cosets of Z by elements in Z. So this includes all cosets of the form NZ, right? Where N comes from Z. So this, if we calculate NZ separately, right? For some N, an integer, for some integer N, this is equal to what? N times M. So times in this case, like I told you earlier, refers to the binary operation over Z, which is addition. M, where M comes from Z now. So N plus M. For any integer M, you are taking all these elements N plus M. What do we end up with? All the full set of integers once again, right? So this is equal to Z. This is equal to Z. So for any N that you take, doesn't really matter. N equals 1. We have the left coset of Z by 1, which is 1Z, is equal to Z. Let's take N equals 2. Once again, 2Z. We've got it to be Z. No matter which integer you pick over here, there is only one left coset, and that is simply Z. So this set contains only one element, that is Z, the set of integers. Now, if you look at these two, the quotient contains only one element. So what does it mean? This is isomorphic to the trivial subgroup of Z, isomorphic to the trivial subgroup of Z, which essentially contains the identity element. So in this group, the identity, because it's a group, identity is in there. When it has only one element, that element has to be the identity. So there is a one-to-one correspondence over here. This is isomorphic to the trivial subgroup. Observe that I'm not saying Z, the set of integers, is isomorphic to the trivial subgroup. No, we are saying the set containing Z. So now in this set, the set of integers is merely an element, which corresponds to 0 on the other set. There are two sets, each containing just one element. Okay? Right. If you have any question, feel free to ask me or even use the chat box. It doesn't really matter. Okay. Then, okay, go to the other definition. Definition, a group we call simple if it is non-trivial. It has to be at least with two elements. It has to be non-trivial and has no proper non-trivial normal subgroups. Let me write it first. A group is simple if it is non-trivial and has no proper non-trivial normal subgroups. So what does it really mean? You have a group, let's take, to understand the definition, G is a group. We know any group has at least one normal subgroup, which is the trivial one. If the group itself is containing just one element, the group is the trivial group, right? And the group itself is normal. So it has G to be normal in itself, and the trivial subgroup, which simply contains the identity element, is also a normal subgroup in G. So what does this definition tell you? It tells you a group is simple. This G is simple if it is non-trivial. So G has to be non-trivial, must have at least two elements, right? It is non-trivial and it cannot have any proper non-trivial normal subgroups. Proper non-trivial normal subgroups. There cannot be there are no uh, n subgroups which are normal in G such that n is non-trivial and is proper. This simply means n is a proper subgroup of G. Because you can always think G is a subgroup of G. G is normal in G. So to make sure that you don't count G as G as a normal subgroup of itself, the definition tells you it's only simple if you have no normal subgroup that is non-trivial and is a proper subset of G, right? Okay, so as an example, okay, let's take any subgroup of prime order. They can't have non-trivial proper subgroups of any kind. Mm, if G is a group of order, then G must be simple. Why is that? Because there can't be any proper subgroup of G that is non-trivial. Any proper subgroup of G that is non-trivial. Why is that? If G is a group of prime order, we have learned the Lagrange's theorem, and it says that if there is a group, if there is a subgroup of this group, and when G is finite, the order of that subgroup must divide the order of G, right? So when G has prime order, the order of G is a prime number. What are the only divisors of a prime number? 1 and the prime number itself, right? So there are no group. In that case, the only subgroups that this group can have are the trivial one and itself. There are no groups in between, so to say, right? So we can argue, we can simply write if H is a subgroup of G, then by Lagrange's theorem, and because we are saying G is a group of prime order, it has the order of G is finite. Then by Lagrange's theorem, order of H must divide the order of G, right? And since order of G is prime, we have the order of H to be either 1 or order of H to be the prime number itself. In other words, order of G itself, right? If the order of H is equal to 1, this simply tells you that H is the trivial subgroup of G. When the order of H is equal to the order of G, this simply tells you that H is actually equal to G. So in any case, we see that there are no other proper subgroups of G, let alone normal subgroups, that are non-trivial. Okay, so if you give specific examples, this is like a generic way to say, we've got Z5, Z7, all these to be, and even the alternating group A3. Why? Because the order of A3 is 1/2, 3 factorial, which is simply 3. and a prime number. So these are some of the examples, some groups which are simple. And then we have a theorem. We will not really prove it, but I'll state it for alternating groups. We have the alternating group AN is simple for all n greater than or equal to 5. In this case, we see this special case for A3. But for any n that is greater than or equal to 5, this is definitely a simple group. Even though the order is not prime, right? Because obviously when n is greater than or equal to 5, the order is not really prime, but the group itself is simple. Okay. Right. Now, once again, we are back to group homomorphisms. Let me state this as a theorem. Let's take phi from a group G to G prime to be a group homomorphism. And then if n is normal subgroup of G, if n is a normal this is how we denote normal subgroup of G, then we must have its image under the map phi, which is phi of n, to be a normal subgroup of the image of G, phi of G, not G prime. We had to be very careful with that one. I'll show you by an example, because phi of n, this image of the normal subgroup under this map, need not be normal in our codomain G prime, but it surely is normal in G's image. So what does it tell you? Homomorphisms preserves normal subgroups between G and its image. G and its image. Okay. Right. And on the other hand, we can also write, if you take a normal subgroup in the image, its inverse image must also be normal in G. Let me write also, if n prime is normal in phi of G, then phi inverse of n prime is normal in G. This must be normal in G. Okay. As a remark, I'll write as a remark, homomorphisms preserve normal subgroups. Between normal subgroups between G and phi of G, right? Now, actually, I think we have previously shown that now we are going to prove that if n is normal in G, its image is normal in phi of G. I think we have previously shown that if this is a subgroup of G, its image is a subgroup in G prime. I think we have done that, but we'll quickly clarify this. Let me write, we have previously shown that N is a subgroup of G, implies phi of N is a subgroup in actually G prime, but simply write phi of G. This we have shown. I think we sometime back when we first started homomorphisms. How do we usually show that a set is a subgroup of a group? A subset of a group is in fact a subgroup by simply using the subgroup criterion. So we can quickly prove this one. First, if we are going to employ the subgroup criterion, we have to show that the given set is not empty. So how do we prove that this is non-empty? Observe that N is a subgroup of G. So it contains, because it's a subgroup, it contains G's identity as well. And we know through homomorphisms, the identity of G will be mapped to the identity of, in this case, G prime. Right? So phi of identity of G, which is equal to the identity of G prime, must be in this set. These are properties of homomorphisms. So because the identity is contained in this, G prime is a group, so the identity is there. It's an existing element. This is not empty, right? So let me write EG is in N. This implies that phi of EG, which is mapped to the identity of G prime, this is G prime, is in phi of N. So this is non-empty. Right? Now, to employ the subgroup criterion, we take any two elements from this set. Let's take A, B to be from this set. Now we will show that AB inverse also belongs in this. Because we are taking A and B from the image of N, this means by definition of an image, right? There are elements in N that are being mapped to A and B through phi, right? So this implies that there exists N1, N2 in N such that A is equal to phi of N1, B is equal to phi of N2. Right? Now to show that AB inverse is in phi of N, we have to, let's find AB inverse. A is given by phi of N1, B is given by phi of N2, inverse of this. It can take the inverse inside. Once again, properties, we've seen this, we've proved this one. N1 times phi of N2 inverse. By the homomorphism property, this can be written as phi of N1, N2 inverse. Now, N1 and N2 are taken from capital N, which is a subgroup of G. Then we know this element belongs in N. So, AB inverse is actually phi of some element that is in N. That is in N. Therefore, this must belong in the image of N. It must belong in the image of N through phi. Therefore, we know by the subgroup criterion that phi of N is a subgroup of phi of G. Right. Now, the normality part we haven't proved before, so that is what we have to show. By definition, right? How do we prove that this is normal in phi of G? We have to show uh, for all, let's say, y in phi of G, and simple n in phi of n, we must show that y inverse of n times y is in phi of n. If you can prove this property for every y and every n that you take from the respective sets, we can conclude that phi of n is a normal subgroup of phi of g. In order to prove this. Okay. So let's pick arbitrarily an element y from phi of g and an element n from phi of n. Y from here and n from the image of the group n. Now, y is actually taken from phi of g. This implies, because it's in the image of g, this means there is some element in this group g that is being mapped to y. And similarly, because n is taken from the image of capital N, there is some element in this set that's being mapped to n, right? Let's take it to be a, because it's in the image. Oh. Then there exists uh, G in G, capital G the group, and simple n in the normal subgroup, normal subgroup of n, normal subgroup n of G, such that phi of simple G is equal to y and phi of simple n is equal to a. Right? Okay. Now let's calculate this. Let's compute the element y inverse a by. This is equal to y inverse. Y is given by phi of g, right? So y inverse is phi of g inverse. A is given by phi of n. Then times once again phi of g. This is equal to, can take this inverse inside and write phi of g inverse, phi of n times phi of g, because phi is a homomorphism, its property allows us to write n times g. Now once again, phi of g inverse, phi of ng. Once again, because phi is a homomorphism, we can write this as phi of g inverse ng, right? Now, this element, what exactly do we want to show? We want to show that this element belongs in the image of n under the mapping phi, right? That means you have to show that this is equal to phi of some element that is in n. Now we have gotten G inverse Ng. And remember, n is a normal subgroup of G. By definition of a normal subgroup, we see that this element belongs in N, right? Since N is a normal subgroup of G, for G in simple G in G and simple N in N, we have, by definition of a normal subgroup, G inverse Ng to belong in N. So that phi of G inverse Ng, which we have to be simply y inverse ay, must belong in phi of n, image of capital N under phi, because some element in n is mapped to this element. And all these, this y, a, they are all chosen arbitrarily from the two groups respectively. Therefore, by definition of a normal subgroup, we have phi of n to be a normal subgroup of phi of g. Now, the other part that I told you, this actually may not be normal in G prime. It's definitely normal in the image of G, but not necessarily in G prime, not necessarily. It's easy to see by an example. To give a counterexample. Let me write phi of n may not be normal in G prime. May not be normal in G prime. Okay, for example, if we consider, let's take our G to be the additive group. No, let's take G to be Z2, right? This contains elements 0 and 1 under the binary operation addition modulo 2. Then let's take our G prime to be S3, the permutation group of order 6, right? And then let's define phi from Z2 to S3 by mapping 0 to definitely, then this has to be mapped to the identity, otherwise this phi will not be a homomorphism. So let's map the identity element 0 in Z2 to the identity permutation in S3, which is denoted by this. And let's map 1 to the permutation 2, 3. Right? So this means phi of 0 is equal to the identity permutation. Phi of 1 is equal to the permutation, which swaps the two elements 2, 3, keeping 1 fixed. Okay, so this is a homomorphism. This is a homomorphism by, if you take phi of, you have three possibilities. You can take phi of 0 times 0, right? Which you don't really need to write down because phi of 0 times 0, if I'll simply write 0, times in this case, when you say times, you're actually referring to the binary operation over Z2. So I'll write addition modulo 2, 0 is equal to what? Phi of simply 0. This is equal to the identity permutation. Now, identity permutation I can write as identity permutation times the identity permutation and replacing this by phi of 0. Now, between these two, we have the composition phi of 0. Why? Composition is the binary operation over the set of the group of permutations because they're essentially functions. Binary operation is composition. So you see, for this element, it's easy to see. Let's do phi of 1 addition modulo 2, 0. Because it's an abelian group, this one, 1 plus 0 or the other way around, we have to get the same thing, right? This is equal to what? Phi of 1. Once again, this is equal to the permutation 2, 3. You can write this as 2, 3 composite with the identity function. So you get phi of 1 composition, phi of 0. For 0, 1 also the same. You can see that it gives you the same. If you do phi of 1 addition modulo to 1, we see that this is 1 plus 1, you get 2. Divide by 2, take the remainder. That is what addition modulo 2 means. You take the two numbers, add them, divide by 2, take the remainder. So this is equal to phi of 0. Right? And this is the identity element. Now you see, if you compose 2, 3, this is actually equal to 2, 3 times 2, 3y. When you take the composition of the two, over here, 1 is fixed. So in the composition, in both permutations, 1 is fixed. Composition also, 1 is fixed. When you go to 2, you start with the right hand, the permutation that's on the right. 2 goes to 3. In here, 3 goes to 2. So ultimately, in the composition, 2 actually is sent to 2. 2 is also fixed. 3 goes to 2, 2 goes to 3. 3 is also fixed. So you see the composition of these two is equal to the identity. This you can write as phi of 1. Phi of 1. So phi is a homomorphism because it satisfies that property and it's well defined as you can see. But when you take Z2 by itself, it is a normal subgroup of itself, right? We have Z2 to be a normal subgroup of itself, right? But if you find phi of Z2, what do we have in here? This is the set containing simply the identity, and it's the subgroup containing the identity and 2, 3, a subgroup in S3. Is this normal? No, it's not. It's not normal. Right? We have seen this by example, but this subgroup, the only normal subgroup in S3 is the one containing identity 1, 2, 3 and 1, 3, 2, which we have seen, right? This is not normal in S3. This is normal in the image of Z2, which is itself, right? Which is itself, but not normal in the codomain over here. In other words, G prime. Okay? All right. If you have any questions, you can always ask me. Right now, for a non-abelian group, we do have uh, two special subgroups. We will actually talk about the center of G, which is one of those, and the commutator subgroup of G. Right? So let's write G to be a let's take G to be a non-abelian group. Right? And then we have a normal subgroup, another normal subgroup of G, Z of, denoted by Z of G, right? This is a normal subgroup in G. This is what we call the center of, how do we define this? Now observe that this could simply be the trivial subgroup of G, right? Now, center of G. How do we define ZG? Z of G. This is defined by all elements Y in G such that YG is equal to GY. This is for all G in G. What sort of elements does it contain? It contains every element in G that commutes with every other element in G. You take now this is definitely not empty, and in a previous example we have shown that this is a subgroup of G as well. In an example I have given you, I remember, when we actually first discussed subgroups. We used the subgroup criterion to show this. Now observe that this is never empty, right? Let me first write. We have proved in a previous class. Abelian. Abelian subgroup of G, right? It's an Abelian subgroup of G. This is never empty. Why? The identity is in there because the identity will commute with every element in G, right? Every element in G. for example, take G in G, we have, by definition of the identity, that is, identity times G is equal to G times the identity. So that we know the identity element is in this, right? We have shown that this is a subgroup of G, but we have never proved the normality condition of this. We have never proved that the center of G is a normal subgroup of G. So that one we will prove. Once again, using the definition of a normal subgroup, let's take any G in G and any element Y in Z of G, right? Because Y is taken from Z of G, then we must have YG to equal GY for every G that you take from the group G, every simple G that you take from the group G. Now we want to show that G inverse YG is an element in this center. How do we do that? Let's calculate or let's compute G inverse YG. This is equal to what? Now, for any G that you take from the group, YG is equal to GY. Now, this specific G is also taken from the group. Therefore, we can commute these two and write G inverse GY. And using the associative property, we see that this is G inverse GY. This is the identity times Y, which is Y. And Y is taken from the center. So this element is in the center of G. Therefore, by definition of a normal subgroup, we have the center of G to be a normal subgroup in G. Now we are once again going back to homomorphisms to discuss the fundamental theorem and every other isomorphism theorem. Okay. Do we have any questions up to this point?
No, madam.
Right. So going back to homomorphisms. Now, take any homomorphism, we have seen that the kernel of that is a normal subgroup in the domain, normal subgroup of the domain. So taking that normal subgroup, we can actually build the quotient group. So in other words, by taking into account any homomorphism, we can always find a quotient group by considering the kernel of that homomorphism, right? Now, in this, what we are going to do is when you have a quotient group, in other words, when you have given a group G, when you have a normal subgroup of it, you can always build the quotient group, right? And given a quotient group, we can come up with or build a natural homomorphism. Earlier, by considering a homomorphism, we gave rise to a quotient group. Now, using a quotient group, we will give rise to a homomorphism, right? So let me write, if phi from G to G prime is a homomorphism. Phi gives rise to a natural quotient G over the kernel of phi. Kernel of phi is a normal subgroup in G, which we have done. Now, we will show that each quotient group or factor group G over H. This is when H is normal in G, gives rise to a natural homomorphism, where in this homomorphism, H is the kernel. Okay. Let me state it as a theorem. Let H be a normal subgroup in G. So let's first write G a group, H a normal subgroup in G. Then gamma, the map from G to G, the quotient G over H, defined by gamma of simple G is equal to G times H, the left coset of H by the element G, is a homomorphism with kernel H. Right. Now you're given a group, H is a normal subgroup of G. So G of H, the quotient group you can define. And we are giving or we are defining a map from G to its to the quotient group G of H. In G, we have all elements in G. In the quotient group, we have left cosets of H by elements in G. So you can naturally define the map, but you have to show that it's a homomorphism. Not only that, the kernel of this homomorphism is simply H. How do we define the map? Take any element in G, you send it to the left coset of H containing that element. Take an element simple G, send it to the left coset of H containing it. And if a left coset is containing that element, you can always take that element as a representative for that left coset. That's why we simply write gamma of G is equal to G times H, because this is the left coset containing G. So you can simply write it as G times H. It could be maybe given by a different representative, but whatever the element that you take from here will be sent to its corresponding or the coset that it belongs to by H. Okay, now first we want to show that this is homomorphism. So, and this is well defined, by the way. Take any two elements, take one element, it will always be mapped uniquely to one coset. Why is that? If you randomly take any two cosets of H in G, there are only two options. They are either disjoint or identical. If they are disjoint, right? So that's why take one element cannot be mapped to two cosets. It will always be mapped uniquely to one coset, right? Because any distinct cosets will always be disjoint. There are no common elements in those cosets. Okay, right. So it's well defined, easy to see. Let's prove that this is a homomorphism. Not only that, let's prove that it's a homomorphism with the kernel H. Okay. To show that this is a homomorphism, let's take G1, G2 from the group, and we need to show that gamma of G1, G2 is equal to gamma G1 times gamma G2. This is what we have to show, right? So let's find gamma G1, G2. This is equal to, by definition of this gamma, G1, G2, H. And this is equal to, by definition of the quotient group, by the binary operation that was defined on the quotient group, we can write this as G1H times G2H. This is equal to what? Gamma of G1 times gamma of G2. Therefore, by definition of a homomorphism, gamma is a homomorphism. Okay, gamma is a homomorphism. Right. So now we want to show that the kernel of phi is actually equal to H. The kernel of phi is actually equal to H. Now observe that you have, this is something that we have proved. Observe that GH is equal to H if and only if G is in H. This we have done, proved some time back. Okay. Therefore, the kernel, when you find it, first of all, it contains all elements in G that are mapped to the identity element in the quotient. What is the identity element in the quotient? It is this normal subgroup H, right? Because H by itself is a left coset of itself by the element. You can pick any element in H to find that, or to simply to reduce it. As a representative for that coset, we usually pick the identity, right? So you take any element in G or every element in G such that gamma of G is equal to the identity element of the quotient. Identity element of the quotient is what? Simply the coset H, right? So gamma of G equals H. Gamma of G is equal to what? Gamma of G, by definition of the function, is given by G times H, right? So gamma of G, I will simply replace by GH. This is equal to H. And from the statement that I made earlier, we know that GH is equal to H if and only if G belongs in H. So what sort of elements do we have in this set? All elements in G that belongs in H. In other words, every element in H. So kernel of gamma is simply H. And we are done with the proof. Okay, with this, we actually go to the first isomorphism theorem. Now observe, I'll first state the first isomorphism theorem and then I'll tell you how we find our specific isomorphism, the required one. First isomorphism theorem or the fundamental homomorphism theorem, I think. Okay, first let's state it. Let phi from G to H, where G and H are groups, be a homomorphism between the groups G and H, then we have the quotient group G over the kernel of phi to be isomorphic to the image of G or phi of G, right? So phi of G is what? Simply, in some cases, you might see this written as image of G. They're essentially the same. Okay, this is equal to what? Every element that are in the range where G is in G. Okay, sometimes instead of phi of G, you might see this image of G. Right. Now, how do we show that these two groups, we understand first of all that these are well-defined groups, because in a previous lesson we have shown that given a homomorphism, the image of G is a subgroup of H, right? So it's a group on its own, the image of G. Not only that, kernel of phi is normal in G, so this quotient is well defined. It's a subgroup of G, right? Okay, so let me write that one also in the proof. First observe that kernel of phi is normal in G, and so kernel of phi is a well-defined group, and phi of G, we have proved this to be a subgroup of H. So phi of G is a group on its own under the same binary operation as H. Okay, now how do we show that these given groups are isomorphic? What do we mean by an isomorphism? So an isomorphism is a bijective homomorphism between the two groups. So we have to come up with a homomorphism between these two groups, which is bijective. What do we mean by bijective? That homomorphism or that mapping has to be a one-to-one and onto function. One-to-one and onto function, right? Now, in order to define that mapping, we go back to this theorem, right? So what does it say? We have from G to G over H, when H is a normal subgroup of G, a well-defined map gamma by sending any element G to its corresponding left coset. Now see, how do we naturally build this function? We have G over here. We have G from G to phi over G, phi of G. From G to its image, we have this mapping phi, right? Which is the homomorphism given over here, right? Instead of taking it from G to H, I will simply take it from G to phi of G, right? It's okay, we can do that. And then the kernel of phi, right? Kernel of phi is a normal subgroup of G. So now we have from G over the kernel of phi, right? From here to here, we have the mapping gamma. How do we define gamma? Gamma of G is simply equal to G times kernel of phi, right? That's how we define the map over here. Gamma of G will be mapped to G times H. H is this normal subgroup, okay? Now, in order to prove that these two are isomorphic, we had to find a map from here to here, which I'm going to simply take as F, using these two. So how do we take an element from here? You take any G from here, it will be mapped to, this G will be mapped to phi of G. This G over here through gamma will be mapped to G times kernel of phi, right? So how do we define this natural mapping? You had to take any element over here and map it to some element over here. What sort of elements do we have in the quotient group? All left cosets of this kernel by elements in G. And so they take this form. So what I'm going to do is, looking at this chart, I will take a left coset, G times kernel of phi, and map it to phi of G. Map it to phi of G. That this seems like the most natural way to do it, right? And with this, you can actually see, now this is not really a part of the proof. You can write phi as the composition of gamma and F, right? So once again, you take any element G through phi, it's mapped to phi of G, right? We don't really know what the rule is for phi. All we know is that it's a homomorphism. So G will be mapped to phi of G, an element in this. Through gamma, this G will be mapped to G times the kernel, right? Its corresponding left coset. We want to find this map F, which has to be a homomorphism, by the way, and also a bijection, one-to-one and onto function. What we're going to do is we take any left coset. So any left coset will be of the form G times the kernel. And the most natural way to do it would be to map it to the element that's corresponding to G in this set, which is phi of G. And we will show that this is a homomorphism. It's well defined, first of all, and is a homomorphism, is also a bijection, right? Okay. Now, this is for you to actually understand how we come up with the map. Leaving this, putting this to a side. Let's write, okay, now let's define F from the quotient to the image by f of gk equals phi of g, where I have simply, without having to write kernel of phi, I will simply denote it by capital K, where k is simply equal to kernel of phi. Right, so it's easy for us to see rather than write curvy. When you write it in this form, it's easy for us to understand. Now we are talking about left cosets of K or the kernel in G, right? So take a left coset, map it to the element in phi of G that corresponds to this representative G, okay? Now, to show that, so let's take, first we will show that F is well defined. To prove that, let's take any two elements from the quotient G1K, G2K be elements in the quotient. Kernel of phi, or you can simply write G over K. Even this curve phi over here, you can replace by K. Okay. Now, we will first show that F is well defined. First, we show that F is well defined, right? How do we prove that a given function is well defined? If you take any two elements from the domain, if those two are the same, right, then the function values must also be the same. In other words, what does it mean to say that a function is well defined? It's uniquely, any element that you take from the domain will be mapped uniquely to some element in the codomain, right? Okay, so let's take, to show that F is well defined, if G1K equals G2K, then we must have f of G1K to equal f of G2K. G1K equals G2K implies, right, This implies that G1 inverse G2 is an element in K. Why do we have this? Now, these are two left cosets of K, one by the element G1, the other by the element G2. If those two are the same, we have done this theorem previously where it says when you take these two representatives, G1 inverse G2 must be an element in K, right? It must be an element in K. This for cosets, we have proved these properties. So I suggest that you go back and go over the properties as well. So it's a property that appears in that section. Okay. If these two cosets are the same, we must have G1 inverse G2 to be an element in K. And observe that K is simply the kernel of phi, right? So I'll write G1 inverse G2 is in the kernel of phi, right? If this element is in the kernel of phi, by definition of the kernel, it says this is an element that's being mapped to the identity in the codomain by F. So we must, by phi, sorry, because it's in the kernel of phi, it's an element in G that's being mapped to the identity in H, the identity in H. So this means phi of G1 inverse G2 must equal the identity of H, right? Now, phi is a homomorphism. So using the homomorphism property, we can write it as phi of G1 inverse phi of G2 equals the identity of H. This we can take this inverse out and write phi of G1 inverse phi of G2 equals the identity. Now what do we do? Multiply both sides or take the product. When I say take the product, I'm actually referring to the use of binary operation over H. Okay. So take the product on both sides on the left by phi of G1. So we have phi of G1 times phi of G1 inverse phi of G2 equals phi of G1 times the identity. This gives you the identity, right? Identity times phi of G2 is simply phi of G2. This is equal to phi of G1 times the identity, which is phi of G1, right? So phi of G2 is equal to phi of G1. By definition of F, phi of G1 must equal, I will simply write the phi of G1 on this side, which you can do. It's G1K is equal to F of G2K. Exactly what we wanted to prove. So F is a well-defined function. Now that we know it's a well-defined function, we have to show that this is a homomorphism. It's one-to-one and non-to. It's a bijective homomorphism. A bijective homomorphism by definition is an isomorphism. In that case, we simply say that these two are isomorphic. So to prove that this is a homomorphism, let's take these two elements G1K, G2K. We have f of G1K times G2K. We have to show that this is equal to f of G1K times f of G2K. Now this is equal to f of G1, G2K. Definition of the binary operation over the quotient group defined on the quotient group. Right? That's how we get this one. So f of G1, G2, G1 and G2 are elements in G. Therefore, G1, G2 is an element in G. So this, by definition of f, ends up being phi of G1, G2. Now, phi is a homomorphism. So we can take the product phi of G1, phi of G2. phi of G1, going back to the definition of f, we see that f of G1k times this is f of G2k. So it's easy for us to see that by definition, f is a homomorphism, right? Now we have to show that f is 1 to 1 and it's onto. F is 1 to 1. Why do we have this? F of G1k equals f of G2k. If f is 1 to 1, we have to show that this implies G1k is equal to G2k. This actually implies phi of G1 equals phi of G2 by definition of f, right? Phi of G1 equals phi of G2. Now what I'm going to do is I will take the inverse of phi of G2 on both sides, right? So we have phi of G1 times phi of G2 inverse. This is equal to phi of G2 times phi of G2 inverse, right? Phi of G2 inverse. Now, this over here is phi of G1. I will take this inverse inside. So we have phi of G2 inverse. Here we have phi of G2 times phi of G2 inverse. Right? What does it amount to be? Because this phi of G1, phi of G2 are elements in H, they're elements in H. This will simply give you the identity in H. So the identity in H. Now this phi is a homomorphism. So using that property, we can write as G1, G2 inverse is the equal to phi of G1, G2 inverse is equal to the identity of H. Now we have an element in G which is being mapped to the identity of H through the homomorphism. So by definition, this element must belong in the kernel. Therefore, we must have G1, G2 inverse to be in the kernel, which is K, right? G1, G2 inverse is in K. This implies G1K must equal G2K. Once again, I'm referring to those properties that we proved for cosets, right? So G1K must equal G2K. Exactly what we want to show. F is 1 to 1. Now to show that F is on to, that means for any element that you take, from phi of G, there must be some element over here which is being mapped to this. Show that F is on to. Let's take Y to be an element in phi of G, right? Then, because Y is taken from the image of G through the map F, right? We must have then, we must have some element simple G in G that is being mapped to Y. Phi of G is equal to 1. Now, let's find f of gk. By definition of the function f, this is equal to phi of g, and phi of g is equal to y. So for any element that you take from the image, that you take from the codomain, you have some element that's being mapped to it in the domain. This function is a onto function. So that F is onto, right? Therefore, we have F to be a bijective homomorphism. F is a bijective homomorphism. And so, by definition, F is an isomorphism. By definition, F is an isomorphism. Therefore, these two must be isomorphic. These two must be isomorphic. Okay. Okay, do you have any questions?
No, ma'am.
Right, then let's do one problem where we can use the first isomorphism theorem. I'll state it as a problem. Let C R denote the set of complex numbers and real numbers, the additive groups of complex numbers and real numbers. Okay. Show that this quotient is isomorphic to R. Okay. First of all, we have to understand that this is a well-defined quotient group. The group of complex numbers under addition, it's an abelian group. So any subgroup of it, specifically R in this case, will be normal because we know any subgroup of an abelian group will always be normal in that group. C is an abelian group. R is a subgroup of it. Because C is abelian, R is normal. So this quotient is well defined, right? Okay, we have to show that this is isomorphic to R. In other words, we have to show if we are going to use the first isomorphism theorem, right? If you compare it with the problem at hand, the first isomorphism theorem tells you if there is a homomorphism between G and H, then G over kernel of H is isomorphic to phi of G. If there is a homomorphism, right? So this is what we are going to do. So to use it, we are going to find a homomorphism from C to R so that we can use in the first isomorphism theorem, prove that C over the kernel of that homomorphism is isomorphic to the image of that image of C under that homomorphism. Right? Okay. And we will show, first let's define the function in Isiva. Now we want to define first of all, we have to somehow find a way to define a function from the the group of complex numbers to R. From the group of complex numbers to R by, in the usual notation, any number in the complex number system takes the form x plus iy. This is how we usually denote a complex number. So through this map, we want to map it to any real number. There are many ways to do it. There are many ways to do it. But what we are going to do in this case is we will set it equal to 1. We'll set it equal to 1. Right? Now, it's easy for us to say that this is a homomorphism. Why is that? Now, what we are going to do is, this is the plan now. We will show that P is a homomorphism. Not only that, if P is a homomorphism, what do we have? Set of complex numbers over the kernel of phi is isomorphic to phi of C. And it's easy to see that this function is onto. This function is onto, right? What does it mean? Any element that you take from here will have a pre-image in C. Will have something that's being mapped to it from C. In other words, if phi is onto, then after this we will show that phi is onto. If phi is onto, we have phi of the set of complex numbers to equal R, right? The codomain, the range will simply be the codomain if it is onto. So the way we have defined this map, it's easy for us to see this is indeed an onto function. For any real number, you can always find its imaginary counterpart. So for any number that pops up over here, it will have a pre-image. This Y will have a pre-image, right? So it's onto. Not only that, we have to show that this kernel of phi, because we want to show complex numbers over R is isomorphic to R, we have to show that the kernel of this phi is equal to R, which is once again not very hard to see. What is the what is the identity in R under addition? It's 0. What sort of elements are mapped to 0? When you have this portion to be 0, because whatever complex number that you take, the imaginary part will be mapped to the y that's in this imaginary part, right? This will be mapped to the corresponding number in R. So this part has to be 0, then only we will get elements that are being mapped to over here. So every other real number will come here. Right? So we will write it in details and we will show that the kernel of phi is simply equal to R. Okay. Phi, to show that phi is a homomorphism, first of all. Let's take x1 plus iy1, x2 plus iy2 elements in the set of complex numbers, and let's find phi of x1 plus iy1 times phi x2 plus I by 2. Now, once again, when I say times, I mean the binary operation over the set of complex, the group of complex numbers. In this case, it's addition. So we put addition over here. Is equal to, this can be written as what? Take the real parts together. So we add component wise, x1 plus x2, then the imaginary ones, I times y1 plus y2. which is another complex number, right? So by definition of phi, this will be mapped to this portion, y1 plus y2. So y1 by definition of phi is what? This is equal to phi of x1 plus iy1. Then y2 is phi of x2 plus iy2. x2 plus iy2, exactly what we wanted to show. Therefore, we can deduce that phi is a homomorphism. Now we have to show that phi is 1, 2. Phi is on 2. So because phi is a homomorphism, let's write from the first isomorphism theorem. We have C over kernel of phi is isomorphic to phi of C. Right. Now we will show that phi is onto. Let's take R any real number or even Y, doesn't really matter. Then if you take R any real number, then we have I times R to be a complex number, right? I times R to be a complex number, and I times R, or in other words, let's simply put it as 0 plus I times R. Then it's easy to see it's in that form, x plus iy, right? And if you map this element through phi, we have 0 plus ir to be mapped to R, right? So it's being, this element is being mapped to R. Therefore, phi is R. Okay. And now, therefore, because this mapping is onto, we must have phi of the set of complex numbers to equal the codomain, which is R. Okay. Right. Now we had to find the kernel. Also, the kernel of phi is equal to all values. It's a subgroup of this additive group of complex numbers. So it takes all complex numbers that are being mapped to the identity in R through phi. So this is phi of x plus I y equals, the additive identity in R is 0. Phi of x plus iy is simply y. This is equal to 0, right? So y is equal to 0. We have this portion to the imaginary part will go to 0. We only have x, where x is an element in R. So we have all real numbers here. The kernel of phi is simply R. Therefore, we have C over kernel of the quotient will be C over R, isomorphic to R. Right. Any question?
Madam, is it necessary to show these steps like one by one, or is it okay to do whatever I see at the
No,
first step?
in whatever, obviously, first thing is we are going to use the first isomorphism theorem. So we must show that phi is a homomorphism, right? But before that, you can show that this is onto, right? You can show that this is onto. Then you can show that it's a homomorphism and the kernel is given by, because the kernel is defined for a homomorphism, then you can show that the kernel is given by this. It doesn't necessarily have to be in this order. Okay, you can first show that phi is onto, then go to show that phi is in fact a homomorphism. It's a well-defined function, because it's very clear in this context, you don't have to show that. You can show on that it's onto first, then it's a homomorphism, then the kernel is this, so that you can deduce at the end, we have the result.
Okay.
Yeah, right. Hmm. Let's do one more problem. Okay, let's do one more problem where we use this. Right now, let's first consider h. Let's take it to be any complex number such that, so let me take this one. Modulus is one. Okay, so this is a subgroup of the multiplicative group of non-zero complex numbers, which you have shown in one of the problems in the first assignment, I think. So I will simply take it to be, we will simply take this to be the subgroup of C star. Let me write C star is the of non-zero complex numbers. It's the multiplicative group of non-zero complex numbers. Right. So the problem is to show that C star, we take the quotient by H. Once again, H is a normal subgroup of this group. This is isomorphic to this to be the multiplicative, where R star is the multiplicative group of positive reals. This is the multiplicative group of positive reals. Okay, so we had to show that these two are once again isomorphic, where H is given by this set. Right. Once again, we are going to use the first isomorphism theorem. How do we use the first isomorphism theorem? We are going to find the homomorphism between C star and R, right? C star and R. And then we will show that the kernel of that homomorphism is H. Okay. Very similar once again, okay? So let's define a map. By taking any complex number and take its substituent. Right, so what you get over here is a real number. How do we calculate it? If any complex number is given by x plus iy, this would simply give you x squared plus y squared, right? Okay. So the it's a real number. First, we will show that this is a homomorphism because it's easy to see. P is a homomorphism since for Z1, Z2 in C star, we have phi of Z1 times Z2. Now we simply write the product because the binary operation is multiplication in both cases, right? This is equal to Z2, and you can simply take the product of the two, phi of Z1 times phi of Z2. By definition, it's a homomorphism. Not only that, this is onto, this is R star, from C star to R star, where R star is actually the multiplicative group of positive reals, all the positive numbers. Okay, so there's that. Now this is a homomorphism, therefore we can, by the first isomorphism theorem, simply say that C star over the kernel is isomorphic to its image through phi, right? So this image we will show that ends up being R star. In other words, we will show that phi is onto. Phi is onto. Okay, and to show this, let any R that you take from positive reals, we have simply phi of R to equal its magnitude, simply R, right? You take the square root of R squared, so you end up with R. And also, now we once again have to show the kernel is simply H. Kernel of phi is given by any Z in the set of complex numbers such that phi of Z is equal to the multiplicative identity of positive reals, which is 1. By definition of phi of, phi of Z, we've got this to be the entire group by definition is equal to H. Therefore, by first isomorphism theorem, we have C star over H to be isomorphic to R star. Okay. Right. With this, we move on to the second isomorphism theorem. And we will use the first isomorphism theorem to prove this. And then we'll do the third isomorphism theorem. Then we will be done with these isomorphism theorems. We can move on to group actions. Okay, let me state it first. Let G be a group and H be a subgroup of G, and N be a normal subgroup of G. H is a subgroup of G and N is a normal subgroup of G. Then we have Hn over N to be isomorphic to H over H intersection N. H intersection N. Okay, it seems like a lot. So what do we mean by Hn over here? I think we did one problem with respect to this one really. Not really the second isomorphism here, but something that we're going to use it. Okay. So Hn is given by this one. So we already understand this, right? Hn, simple H times simple N. When I say times, that refers to the binary operation in G because these two are subgroups in G, right? Okay. So now, and at the same time, we saw that, let me quickly, no, let me write it over here. You can go back and refer to that one. We have already proved. Let me write in my proof. We have already proved that N is a normal subgroup in Hn, and this is a subgroup in G, right? This we have proved in that problem that I showed you just now. And not only that, we have proved that H intersection N, when these two are subgroups of G, when we say N is a normal subgroup of G, it's a subgroup that is normal, right? So when these two are subgroups, their intersection is also a subgroup of G. So we have already proved that this intersection is a subgroup of G. Not only that, we have proved that this intersection is uh, now this intersection is a subgroup of, no, let's get to that part later. Let me write this one also. Also, we've proved that for H n subgroups of G, H intersection N is also a subgroup of G. Right. Okay, so we have to show that Hn, when you take the quotient of this, Hn over N is isomorphic to H over H intersection N, right? Because N is a normal subgroup of Hn, this quotient is well defined, right? This quotient group is well defined. So what we are going to do first is we will find or we will define a map from H to this quotient, right? And then we will use because now if you compare these two, this is a well-defined quotient. What we are going to do is we will define a homomorphism, a map which we will prove a homomorphism from H to this. Then we will use the first isomorphism theorem to show that H, when you take its quotient by the kernel, is isomorphic to this one. So we understand in that case, the kernel has to be this intersection, which we will prove, right? Okay. Therefore, because of this, we have Hn over N to be a well-defined, quotient group. It's a well-defined quotient group. Okay, first we define a map phi. Let's define a map phi from H to this quotient by taking any element over here. What sort of elements do we have here? We have left cosets of n by elements in Hn, right? Left cosets of n by elements in Hn. So what we do is we will take an element in H, send it to the corresponding quotient, corresponding left coset Hn. Why do we have over here H times simply n? If you take an element in H, this H will be an element in Hn as well, right? We actually went over that when we did the problem, because Hn is simply containing all elements H times n, where H comes from the subgroup H and n comes from the subgroup n, right? So we see that H is a subgroup of Hn as well. Why is that? Because n is a normal subgroup, so the identity is contained in there. So for any H that you pick, if we simply pick the identity from n, all elements for E in n, H times E is simply H, E is in Hn, right? So you take any H from the normal subgroup n, we pick the identity. Identity times any element in H is that element. So any element that you take from the subgroup H will go in this subgroup Hn. Therefore, H is a subgroup of Hn. Okay. So any element that you take from over here, there is a natural way for us to map it to the corresponding coset H times n, because H is contained in Hn. Okay, right. So now we have this. First, what we are going to do is we will show that phi is an onto. We have to show that it's an onto, otherwise we won't be able to say that this is isomorphic to, this is isomorphic to Hn over n. P is an onto homomorphism whose kernel is H intersection n, whose kernel is H intersection n. Okay, first we will show that this function is well defined. Okay, phi is well defined as if you take H1, H2 from H1 equals H2 implies, H1n equals H2n. If they are the same element, these two cosets are also the same, right? This implies that from the definition of phi of H1 is equal to phi of H2. So this is a well-defined function. Now we will prove that phi is onto. And we will go in that order. Let's prove phi is onto, then a homomorphism. To prove that phi is onto, let's take an element y in our codomain, which is Hn over n, right? Hn over n. Now we are taking y from this quotient group. Then Y must equal some left coset of n by elements in Hn, right? So Y must equal Hn times n for some H in capital H and simple n in n, the normal subgroup, right? This is equal to H times n, and you can simply write now this n will be absorbed in here. Why? Simple n is taken from n. Therefore, this coset is simply equal to n, which once again we have seen. H times n, this is equal to what? By definition of phi, phi of h for this particular h, for some h in h. Therefore, for some h, for any y that you take from the codomain, you can always find some h that will be mapped to this particular element. Okay, therefore it's onto. Now we have to show that phi is a homomorphism. Phi is a homomorphism as phi of h1, h2 is simply equal to h1, h2, n. By definition of the binary operation defined over quotient groups, we see that this is h1 times n, h2 times n. This is equal to, by definition of phi once again, phi of h1, phi of h2, right? Therefore, by the first isomorphism theorem, we have H over the kernel, we had to show kernel of phi is isomorphic to image or phi of H, which is equal to, because phi is onto Hn over n. Now we have to show that the kernel of phi is actually equal to H intersection n. So it remains to prove that. Right. So now let's write kernel of phi. This is equal to all elements H that we take from the group capital H, which are being mapped to the identity element in the quotient, right? So phi of H that is being mapped to the identity element in this quotient group. What is the identity element in the quotient group? It's this normal subgroup, which is n, where phi of H is equal to n. And we know by definition of phi of h, this is simply equal to h times n, and it's equal to n. In this case, what does it mean? We take all h in h such that h is also in n, because h times n, this coset is only equal to n if this representative is inside n. So now we are taking elements that are both in h and n. So what we have is the intersection of h and n. Therefore, we conclude Hn over n is isomorphic to h over the kernel, which is h intersection n. Okay, any question? Any questions? No.
No, madam.
Right. Then we will do the third isomorphism theorem and be done with it, I guess. Once again, we are actually going to use the first isomorphism theorem to prove this. Okay. Third isomorphism theorem. Let me state it first. Let's take G to be a group. Let G be a group and H be a normal subgroup of G. K also be a normal subgroup of G. Such that H is a subgroup of K. Then we have, now see, H and K are normal subgroups of G. So the quotient G over H, G over K, quotients that we take by H and G over, H and K over G are well defined. So we prove that, so the third isomorphism theorem tells you that then the quotient that you take from G over H over the quotient group G over K is isomorphic to, okay, no, let me rewrite it. G over H over, this must be K over H, isomorphic to G over K, isomorphic to G over K. Okay, once again, we are going to use the first isomorphism theorem. So what are we going to do? We are going to define a homomorphism from the quotient group G over H to the quotient group G over K. Now observe, H is normal in G, K is normal in G. H is a subgroup of K. When H is a subgroup of K and H is normal in G, H must be normal in K as well. H must be normal in K, right? Because the normality condition is satisfied for any G that you take and for any H that you take, G inverse HG must belong in H, right? Because that simple G is taken from anywhere in the group. For any K that you take, where K is a subgroup of G also, this works. So H is a normal subgroup in K as well. This quotient is also therefore well defined. What we are going to do is we are going to define a map from this quotient group to G over K, the quotient group. Show that it's a homomorphism. Show that it's onto. Then we will show that the kernel ends up being K over H. Okay. So all these proofs are somewhat similar, right? So proof, let's take, let's define phi from G over H to G over K by phi of elements are left cosets of H in G. So let's take any generic left coset and we will map it to the corresponding left coset of K in G. So what I mean is with respect to this representative simple G. So I'm going to map this to GK. Now this is well defined, which we will prove. Then phi is well defined. So let's take any two elements first of all. Let G1H, G2H be two elements that are picked from the domain arbitrarily chosen. Phi is well defined as G1H equals G2H implies G1 inverse G2 is in H. This implies G1 inverse G2 is in H, and this implies because H is a subgroup of K, G1 inverse G2 is in K. That is because H is a subgroup of K. Right? Now this implies that G1K is equal to G2K, which in turn implies phi of, if you look at the definition of phi of G1H is equal to phi of G2H. Exactly what we wanted to show. Now we will prove that this is an onto function. So let's take any element from our codomain. Let's take gk from G over K, where G is in G. Right? Then for this particular G, we have the left coset of H in G. This is an element in this quotient. And we have phi of GH to equal, by definition of phi, G of K. So no matter which element that you pick from the codomain, this representative will yield another coset of H in G, which will in turn be mapped to this element that we first picked from the codomain. So we see that phi is onto. Now we have shown that this is well defined onto. We have to show that it's a homomorphism. It is a homomorphism. Why is that? It satisfies that homomorphism condition if we take G1H times G2H. This simply, before doing anything, if we consider the definition of quotient group, this tells you this is equal to G1, G2 times H. Now definition of phi tells you you can write G1, G2 times K. Once again, definition of the quotient group yields that this be written G1K times G2K, right? G1K is what? Phi of G1H times G2K is phi of G2H. Therefore, we see that this is a homeomorphism. Now, we will show that the kernel, before we use the first isomorphism theorem, let's find the kernel, because we want to show that the kernel is actually the quotient group K over H. The kernel of phi is equal to every element in the domain that will be mapped to the identity in the codomain. Identity in the codomain, which is G over K, is simply K. So we write GH taken from this quotient group, phi of GH, the identity in the codomain, the group is simply K. Now, GH, which are taken from the quotient G over H, phi of JH is simply GK, the way we have defined this. This is equal to what? G of H in G over H, where GK equals K, meaning G belongs in K. So the cosets of H by the element G, where G is taken from K. In other words, GH, where G is taken from K. What do we have over here? Quotient K over H. Therefore, by first isomorphism theorem, we have G over H quotient by its kernel, which is K over H, to be isomorphic to the image of phi, G over H, which is simply G over K. Okay, so that would be the end of all these isomorphism theorems. Do you have any questions?
No, madam.
Right, then let's end the session and we'll start group actions the next time.